Hello, Expo Cannabis Argentina. I'm Dr. Dustin Sulak, and it's an honor to present to you today. I wish that I could be with you in person, hopefully next year. I haven't ever visited your country, and I would love to do that. In the meanwhile, I hope that you enjoy this presentation on the acidic cannabinoids, a topic that has become very important in my clinical practice that a lot of people aren't talking about in regard to how to take care of patients and how to take care of ourselves with cannabis. So my background is that I'm a general practitioner. I've been practicing for the last 12 years in Maine, United States, which is in the northeast part of the country. And I attract patients from every other field of medicine, and I'm typically treating refractory cases in adults and in pediatrics. And I've been surprised and made some interesting discoveries that have been confirmed by the research regarding the use of acidic cannabinoids. And so that's what I'm excited to share with you today. The title of this presentation is Acidic Cannabinoids, Inactive Precursors or Powerful Therapeutics. And that's because previously it was thought that these compounds were simply the precursors of the neutral or decarboxylated cannabinoids that we know so much more about. But what we've been finding both in the clinic and in the research is that these are compounds that must not be overlooked because of their therapeutic potential. So in this presentation, I will show you the difference between the acidic and the neutral cannabinoids, and then go over some preclinical studies, meaning animal studies, on their therapeutic effects and their mechanisms. We'll look at pharmacokinetic studies in both animals and humans. This describes how the acidic cannabinoids are absorbed and metabolized in the body. We'll go over a little bit of human clinical evidence that supports the use of these compounds, and then my strategies for clinical use and for taking care of oneself. So to begin with, a lot of people aren't aware that the cannabis plant does not produce THC and CBD and the other phytocannabinoids, meaning plant-derived cannabinoids that we're the most familiar with. Instead, the plant produces the precursors to these compounds called THCA or CBDA. And the A stands for acid because these precursors have a carboxylic acid group on the molecule. And so I can show you in this slide here that this is, for example, CBGA, this compound. It's the precursor cannabinoid that all the other cannabinoids are derived from. In the plant, this is converted into THCA or CBDA or any of the other acidic cannabinoids like CBCA. But what you can see here is that this carboxylic acid group, when this compound is heated, it leaves the molecule as a carbon dioxide, and now we have the decarboxylated or neutral cannabinoids. So you can see that THCA turns into THC and CBDA turns into CBD and so forth. So even in a very fresh sample of cannabis, like this is a picture of a flower of cannabis that's still growing on the plant, you'll be able to find trace quantities of THC and CBD, but the primary form that these will be found in is THCA and CBDA. And then over a period of time, depending on the temperature that that flower or that material is stored at, there will be this gradual conversion, this decarboxylation. And what I'm showing here on the bottom right are the time and heat curves of decarboxylation, in this case, from THCA to THC. And so you can see if you're working with a higher temperature, you need much less time to make that conversion versus a lower temperature could take quite a long time. In vitro, meaning preclinical studies using cells and not real animals, and also ex vivo models where animal tissue has been removed and studied of inflammatory bowel disease have demonstrated anti-inflammatory effects with THCA without the biphasic pro-inflammatory effects seen with other cannabinoids like CBD. And so what this means is that in this model, using CBD, there can be a dose that actually improves inflammation, while a much higher dose makes the inflammation worse. Compared to THCA, which was shown only to improve the inflammation and not make it worse, even at a higher dose. And this is a trend that comes up again and again with some of these acidic cannabinoids in comparison with the neutral ones. It has been shown in one study that THCA acts as a positive allosteric modulator. And this is very exciting and important. And I'll explain what this means. The CB1 receptor is constantly being stimulated by our endocannabinoid system when we need it to be for the regulation of neurotransmitter release, the regulation of inflammation, of gut motility, of pain signaling, of so many different things in the body. Our system is already using this receptor, targeting it and turning it on and off when it needs to. Scientists have been searching for a long time for a positive allosteric modulator of this receptor, which would basically increase the intensity of that signaling. But unlike THC, it doesn't signal the receptors directly. So this is a way of working with our own healing system and enhancing the activity that's already there in our endocannabinoid system. So this is a very exciting mechanism of action of THCA. Now, there are some similarities between THCA and THC. And these similarities are mostly around the ion channels. So these are receptors on the cell membrane that open and close ion gates, such as TRPM8, TRPA1, and TRPV4. And I'm not going to get into a lot of details on these receptors, but a lot of them have to do with the perception of pain and heat and cold, and as well as inflammation. There's also important to remember that ethnobotanical and anecdotal reports of the healing properties of cannabis tea are likely attributed to THCA. And we'll talk more about cannabis tea, but essentially the temperature of the hot water used to brew the tea is not enough to decarboxylate much of the THCA. A little bit might get decarboxylated, but not very much. And the THCA is so soluble in water, more soluble than the THC. So in most cases, the therapeutic effects attributed to cannabis tea are related to THCA. Another thing that's important to note is that it is impossible to have a pure THCA product. Even when stored in cold temperatures and processed very carefully, it's been shown that there's always at least a tiny, tiny amount of THC present. Now, a lot of people looking at these levels would think, oh, if it's 99% pure THCA or 99.5% pure THCA, what could that little bit of THC be doing? Could it really be a confounder? And a lot of people would think no. But I like to point out that there are a number of studies, 3 in particular on this slide, that have shown that tiny, tiny doses of THC in animal models have been able to have important physiologic effects, like protecting mice against the damage of a heart attack, protecting the liver in mice against the damage of an ischemia reperfusion injury, which is a classic model of liver injury. And also this very, very small dose of THC has been shown to turn on protective signaling molecules in the brain. So whenever I'm working with THCA and impressed by what I'm learning about it, always in the back of my mind, I'm wondering, could these ultra low doses of THC be playing a role in the activity of THCA? And the emerging evidence is suggesting that in some cases, both are needed to work together to produce the best outcome. One of the other things that's been shown to be distinct about CBDA is that it can inhibit the COX enzyme. COX is an enzyme in the body that builds pro-inflammatory molecules, and it's a very common target of drugs that are anti-inflammatories. For example, the non-steroidal anti-inflammatory drugs. And so in this preclinical study, you can see that CBDA, CBD, THCA, and THC were all compared to the drugs indomethacin and diclofenac. These are both COX inhibitor drugs that are available for human use. And you can see the potency of CBDA in inhibiting the COX-2 enzyme was really pronounced. That was very different from the other cannabis-derived compounds and very comparable to diclofenac, which is known as a strong COX-2 inhibitor. So it looks like CBDA provides this additional anti-inflammatory activity by inhibiting COX-2 and to a lesser extent, inhibiting COX-1. Now let's move on from nausea to some data on liver injury. So this was, so the background is that chronic liver disease can be caused by things like viral hepatitis, alcoholic liver disease, but also non-alcoholic fatty liver disease, which is really a metabolic disorder. And obesity is a major risk factor for this non-alcoholic fatty liver disease, which contributes to the development of obesity-related complications like type 2 diabetes, dyslipidemia, so bad blood lipids, hypertension, high blood pressure, and cardiovascular disease. And this is a vicious cycle because having these complications tends to make the liver function worse. It worsens the non-alcoholic fatty liver disease, and you get this vicious cycle of perpetuation of the liver and metabolic dysfunction. So this study, again, looking at rodents, tested a classic model of liver injury called the CCL4 liver injury. And so what I'm showing here is the ability of THCA to attenuate some of the damage to the liver in this model. And so you can see here, looking at fibrosis. So fibrosis is the scarring in the liver. And when this liver irritant, this liver toxin is administered, you can see compared to control, the scarring goes way up. When THCA was used, and this time in moderate doses, not ultra low doses, you can see that 20 milligrams per kilogram decreased the scarring to some extent, and the higher dose 40 decreased the scarring even more. So it seems to have a liver protective effect and reducing scarring. And then when looking at how is it acting, again, I hope you're expecting to see some anti-inflammatory effects, because this keeps coming up with THCA, that it works as an anti-inflammatory. And so the researchers noted that interleukin-6 gene expression, this is a gene that produces a pro-inflammatory molecule, it was reduced by THCA at both doses. Interestingly, even a stronger reduction at the lower dose. Interleukin-1B gene activation was also decreased by THCA, as was tumor necrosis factor alpha. This is the one that I described before. So it looks like THCA is protecting the liver by influencing the expression of genes, likely by acting on that nuclear receptor, and decreasing the expression of genes that create inflammation, thereby reducing the overall inflammation, and then the liver is experiencing less damage because of less inflammation. Now, these researchers went on to a different model of liver injury, one that's probably more relevant to humans, which is the obesity-inducing diet. And so rodents were fed one of two diets, what's called the control diet or the high-fat diet. And you can see the breakdown of the macronutrients with the high-fat diet having higher levels of fat and lower levels of carbs. So it was a higher calorie diet. And here we can compare the body weight of the rodents on the control diet and the high-fat diet. And you can see that after 15 weeks, the high-fat diet had gained more weight. They were fatter rodents, and that went up to about 18 weeks and then stabilized. So looking at the liver of these animals, you can see the control diet did not have any fibrosis. These animals did not have liver scarring. And you can see that here in the fibrosis area. Compared to the high-fat diet at 15 weeks, you can start to see the scarring in the liver. It looks quite different. And then that gets worse and worse over time at 18 weeks and at 23 weeks. So even though they're not becoming more obese, their liver is becoming more and more fibrosed, more and more scar tissue there. Now, what happens when THCA was added to this mix? Well, you can see that for one, the body weight in the rodents was reduced. So after they had already been fed the high-fat diet and had gained weight, giving them THCA actually caused them to lose weight compared to the high-fat diet alone or the control diet alone. Very interesting that THCA was able to reduce the weight and to some extent reduce their food intake. So they were eating a little bit less. Also interesting is that the fat mass decreased when THCA was used, and the lean mass did not decrease. It was stable. And so again, looking at an anti-obesity agent, this is always important, not just to reduce food intake or reduce body weight, but to reduce the fat portion of the body weight while maintaining the lean muscle mass. So if this translated to humans, THCA would be very exciting as a body weight strategy and a body composition strategy for people dealing with obesity. Also, THCA was shown to reduce the blood sugar levels of the rodents that ate the high-fat diet. This red line is the THCA compared to the high-fat diet without THCA. And so again, for those experiencing pre-diabetes or diabetes, reducing blood sugar is very important, as is reducing insulin levels. One of the drivers of diabetes is insulin resistance. And here you can see that there was less insulin resistance based on lower insulin levels in the rodents that were treated with THCA. Also lower triglycerides, which is fat in the blood. So altogether, these metabolic parameters really improved with treatment with a moderate dose of THCA that was injected into the abdomen of these rodents. Another measure of this study looked at the T lymphocytes in the liver. These are immune molecules that can lead to inflammation and scarring and damage. And again, here you can see that compared to the control diet, the high-fat diet had a lot more of these lymphocytes. They're staining in brown here. You can also see the evidence of scarring. But when THCA was administered, the level of lymphocytes was much less, almost back down to the control level here with the normal diet. Macrophages are another class of immune cells that contribute to this inflammatory process in the liver. You can see that THCA decreased the level of macrophages. And then here's just another picture of the fibrosis reduced by THCA. So the previous one that I showed with fibrosis had to do with the carbon tetrachloride injury, the CCl4 injury, but this one shows the injury related to high-fat diet. So also attenuating the liver injury from the high-fat diet. So very exciting for THCA as a potential treatment in obesity, in diabetes, in liver disease. Again, I point out that in all of these rodents, they were exposed to tiny doses of THC because you can't have THCA without THC. And if you look at this older study from 2015, you can see that tiny doses of THC were shown to protect the liver. I had mentioned this earlier. So is the THC a confounder? It very well may be, and it's almost impossible to tease that apart, but it looks very impressive using THCA at those doses. Now, here's another study looking at THCA, again in rodents, on the effect of fatty mass and metabolic disease, again created by diet-induced obesity. What these researchers focused on is a nuclear receptor called PPAR gamma. So again, this is another receptor on the nucleus of the cell that controls transcription. And it's a common target of diabetes medications. There's a whole class of diabetes drugs called the glitazones that are full agonists of this receptor. They turn it on strongly. They've been used for decades in the treatment of type 2 diabetes, but their use has decreased because one of their side effects is bone loss and osteoporosis. Now, because THCA is not a full agonist, it doesn't really turn those on fully. It just gently turns them on a little bit. These researchers were interested in, could we get the same benefits that we get from those drugs without the adverse side effects on the bone loss if using THCA. So they tested this in rodents over 12 weeks. So the rodents eat the high-fat diet for 12 weeks, and then they receive the THCA for 3 weeks after that. What they found is that THCA is a partial agonist with low adipogenic activity, which means it turns on PPAR gamma. It does not create more fatty tissue. THCA actually enhanced the growth of bone, the osteoblastogenesis in bone marrow derived mesenchymal stem cells. So this was kind of a petri dish study, but these are the cells that build bone. And while some of these drugs would be shown, some of the drugs that target PPAR gamma would be shown to reduce bone, these actually increase the cells that build bone, which is a very promising finding. And in the rodents, THCA was shown to reduce body weight gain, reduce fat mass, reduce fatty liver. These are similar to the findings in the previous study that I showed you. THCA was shown to improve glucose tolerance and insulin sensitivity again. It was shown to induce browning of the fat. So most of us think of fat as a storage organ, something that just stores calories and stores energy. And that's the white adipose tissue, the white fat. Whereas in certain conditions, especially when exposed to cold, some mammals will turn their white fat into brown fat, which is the process of more mitochondria growing in the tissue, and it becomes a heat-producing tissue. So it actually burns energy instead of storing energy, something that would be very good for individuals or animals that are obese. And THCA was shown to induce browning of the fat. And so, this slide didn't come out great, but just in general, what we can see here is that via the PPAR gamma receptor, when THCA was given to lean mice, it increased thermogenesis, which means it made them heat up more. They produced more heat and burned more calories, but their weight didn't change. In the high-fat diet obese mice, THCA had that same effect of increasing the heat production, but it made them lose weight, it decreased their inflammation, and it decreased the fattiness in their liver. I know every time I talk about THCA having some benefit, I switch back to THC, but it is worthwhile noting that THC, not in ultra low doses, kind of in the moderate dosing range, was also shown to reduce weight gain, fat mass gain, and energy intake in rodents that were given a high-fat obesity-inducing diet. And that THCA, in this study, THC didn't slow them down or change their gut transit or anything like that. But what was really interesting is that when rodents are fed the high-fat diet, not only do they become obese, but the composition of their gut microbiome changes to what's considered an obese microbiome. THC was also able to prevent that change. Now let's move on from liver disease, metabolism, and diabetes and obesity to pain and inflammation. This is another rodent study that looked at the effects of THCA on inflammation as well as nerve function, again, via this nuclear receptor, PPAR gamma. Preclinical data has suggested that agonists of this receptor not only can help with diabetes, but can also help with arthritis by reducing disease severity, by reducing the inflammatory cells, the cytokines, which are the signaling molecules that create inflammation, and in the end, by preventing cartilage and bone loss. There's been human clinical trials showing that this diabetes drug, this type 2 diabetes drug, can, via the same receptor, alleviate the symptoms of rheumatoid arthritis in human patients. It's also been shown that CB1 positive allosteric modulators, and again, THCA seems to be one of those based on a little bit of evidence, which needs to be confirmed, that CB1 positive allosteric modulators can produce analgesia, so they can relieve pain, including neuropathic pain, without causing any impairment or any of the downsides of using THC. And so what happened when rodents were administered collagen, and so they're injected with collagen, which is a model of arthritis. It causes a lot of pain and inflammation in the feet. You can see here's the control foot, the hind paw, with no treatment. With the collagen-induced arthritis, you can see quite a lot of swelling there. When THCA was given, it didn't change. It actually prevented the collagen-induced inflammatory effects. And that was somewhat attenuated by a CB1 antagonist, that would be this picture, as well as a PPAR gamma antagonist. So it looks like the mechanism of action involves both of these receptors, CB1, which might be from that tiny amount of THC in there, or it might be because it's a positive allosteric modulator of CB1, as well as PPAR gamma, the nuclear receptor that controls the transcription of genes related to pain and inflammation. So you can see on the bar graphs, the inflammation was much less with the THCA, as well as much less cartilage damage with THCA. And then when the researchers looked at the inflammatory molecules, some of these should be familiar to you: interleukin-6, tumor necrosis factor alpha, and interferon gamma. Again, you can see that THCA, compared to no treatment, significantly reduced these levels of inflammatory molecules. So another example of an anti-inflammatory effect, but this time instead of in the liver, we're looking at a model of arthritis and cartilage damage. Moving on to another study, this time that combined some of these compounds together. This looked at CBDA and THC in a similar model of pain and swelling in rodents. And so various doses of CBDA, CBD, and THC were administered before, either by injection or administered orally before or after the injection of the carrageenan, which, and I think I misspoke earlier when I said collagen. It's carrageenan is the inflammatory irritant being used in these models. And so let's take a look at the results. So when CBDA was given by injection pre-treatment, you can see this tiny dose, 10 micrograms per kilogram, significantly reduced the hyperalgesia, which is the increase in pain. So it blocked that sensitivity to pain when given after the when given before the treatment. You can see that that effect persisted 180 minutes later, and it persisted 360 minutes later. It also reduced edema, meaning inflammation, but that was less profound than the reduction in pain. Now, over here, we can see CBDA that was administered after the treatment instead of before the treatment. And you can see that the results were less impressive. And so, this 10 micrograms of CBDA dose seemed like it almost made a statistically significant reduction, but not quite. And so in this model, CBDA really shined when it was given before the injury. Something I found really interesting though here, so this is pre-treatment with CBDA and THC, not THCA, keep in mind, just CBDA and THC. And so you can see this is a measure of pain. And so you can see the pain threshold in the group that was not given any treatment, just given the carrageenan to induce the inflammation. 100 micrograms per kilogram of THC did nothing to reduce the pain. 0.1 micrograms per kilogram of CBDA looks like it started to do something, but it was not statistically significant. But combining these two ineffective doses, again, of CBDA and THC this time, reduced the pain signaling quite a bit, and that persisted at 60 minutes. So again, I mean, we just see this over and over again, that these very low doses of these compounds that might not be effective on their own, when they're combined together like they are in the cannabis plant, they have some special effects. And this is what patients tend to experience. They're not using single compounds, they're using the cannabis plant, which includes low levels of many of these compounds, especially when the plant is not overheated. And so this is, again, why I'm emphasizing that these compounds are important, and it's beneficial not to convert all of the acidic cannabinoids to their neutral counterparts. This was a rodent study, so now we're moving from pain and inflammation to seizures. And so this was a study that I'm just going to go over briefly, that looked at not only how are these acidic cannabinoids, in particular CBDA, how is CBDA absorbed both into the blood and into the brain, and what does it do in a seizure model, a mouse model of Dravet syndrome, which is a devastating seizure disorder that's highly resistant to treatment. And so I'll just point out here that, and we can look over here at CBDA, the dose that was used produced 29 micrograms per milliliter in the plasma, which is a kind of a moderate plasma level of a cannabinoid, certainly physiologically active based on other studies. But in the brain, it only produced 2 nanograms per milligram. And so when they did the math, the brain plasma ratio is 0.04. What this means is that very little of the CBDA that's in the blood is getting into the brain, extremely low amounts. And this study also was unable to detect any THCA getting into the brain, something that we're going to come back to in a little bit, because THCA can have anticonvulsant effects, but clearly in this animal model, it didn't make it into the brain at a significant level. So what they showed, though, in this study is that even though CBDA didn't really get much into the brain, it still had anticonvulsant effects at both 10 and 30 milligrams per kilogram. The same model looking at CBD required 100 milligrams per kilogram. This is basically the temperature that these animals were able to tolerate before they had a seizure. In this mouse model, exposing the rodents to high temperatures creates seizures. And so you can see CBDA was effective at decreasing the seizure threshold at over 3 times the potency. Well, actually, really at 10 times the potency of CBD. So 1/10 of the dose was required compared to CBD, even though very little of it is getting into the brain, which again suggests that it's more potent. Now, historically, back in 1979, there was an animal model study published of many of the cannabinoids and looking at what they could do for, this is a different seizure model. It's the MES test, which is an electric shock type of a seizure model. And what they found was that THCA, 2 different versions of it, were effective, but only at high doses, which is interesting because I've seen extraordinarily low doses effective in my clinic, but I suspect these researchers didn't test those very low doses. Now, there was another study from the same group out of Australia that looked at both THC and THCA in the same, in several seizure models, but this is a different one that we haven't talked about yet. And what they did was kind of realistically, they made a mixture of 97% THCA with 3% THC. So this reflects something that you could produce at home or find for sale, especially if it was a product that was refrigerated. And they compared that with pure THC. And what you can see here is that the seizure threshold was significantly raised, elevated in rodents that received this mixture of THCA and THC, as well as a higher dose of the mixture of THCA and THC. When given alone at the same doses, THC did not have this benefit. So one would think, oh, it's probably THCA that's doing most of the work here. Again, interestingly, if you look at the plasma concentrations of THC and THCA, you can see that the animals that received both the THCA and the THC, they had higher levels of THC in their blood. And what this suggests is that when THC and THCA are administered together, because they follow some similar metabolic pathways in the body, the THCA is actually preventing some of the breakdown of THC. And so now we have 2 mechanisms for how THCA can enhance THC. It can slow its breakdown, and it can act as that positive allosteric modulator, which could make the receptors and the effects on the receptors stronger when THC is present. And then very interestingly, this dose that was able to raise the seizure threshold did not produce any detectable levels of THC in the brain. There was probably a little bit in there, but the scientists could not detect it. And it produced only very, very low levels of THCA in the brain. So how are these working at this dose is a very interesting question. The researchers strive to get a 100% pure THCA formula. They came very close. And when they tested it at around the same dose, they found 0 effect on seizure threshold. So what this is suggesting is that this tiny amount of THC that was present, even though it was so small, it did not show up in the brain at all, that this was important for the activity of THCA. I know it's very complex, but the same message comes again and again and again, suggesting that it's important to use these compounds together, and we shouldn't necessarily be striving to isolate them and use them on their own. I'm going to just now talk a little bit more about absorption into the body. And one route of absorption that I found interesting is transdermal. So it turns out that these compounds can get absorbed through the skin. This was a test in dogs looking at a product that had roughly equal portions of CBD and CBDA with equal but very low doses of THC and THCA. This ointment was rubbed into the ears of the dogs twice a day for 2 weeks. And what they found was that at both week 1 and week 2, the blood levels of CBDA were much higher than the blood levels of both of CBD and THCA. So it really looks like CBDA has good transdermal absorption, at least in dogs, which would likely translate to humans, but of course the study needs to be done. And these authors suggested that CBDA may be a better choice for clinical study of local and systemic disease using transdermal skin absorption in veterinary medicine. And I would also suggest that it could be useful in human medicine. Another little tidbit on the absorption of these compounds has to do with CBDA being absorbed in very high amounts when taken through the gut. And so these researchers looked into, well, how is this happening? Why is so much CBDA getting absorbed? And what they studied was this full spectrum cannabis extract that, as you can see, had a little bit of everything, but it had not been exposed to much heat. And we know that because it had high levels of CBDA and high levels of THCA. And they compared this full spectrum aspect when administered to mice and testing the blood levels of these compounds in the mice. They compared that to administering these compounds individually. And there was a real surprise here, because comparing CBDA in the extract to CBDA given alone, you can see that much, much more of the CBDA was absorbed when given as an extract. That was not the case for CBD, and we wouldn't expect it to be the case. Typically, pure compounds can get absorbed better than compounds that are kind of combined with many other similar molecules, because they would compete for absorption. That was not the case with CBDA. You can see that it was the case for CBDVA, CBGA, basically all the other ones they tested. The pure compound was absorbed better than the mixture and the full spectrum extract. So what's going on here? Well, these researchers looked at something in the intestinal wall called the ATP binding cassette transporters. And there's 2 types of transporters, the P glycoprotein and the breast cancer resistance protein, BCRP. And what they found was that this BCRP transporter, and so just to orient you, this part of the slide here is the inside of the intestine, and this part is the blood. And basically, when CBDA is interacting with these intestinal cells, it starts getting absorbed, but then it's kicked back out into the intestine. So less of it gets absorbed, and you have higher levels of the intestine. And this is true with the other cannabinoids. What these researchers found, though, is that especially in the presence of CBG and THC, 2 neutral cannabinoids, this blocked the activity of the BCRP, the breast cancer resistance protein, allowing for much more CBDA to be absorbed. And it was significantly higher, as you saw in this previous slide here. The CBDA levels were so much higher than the pure extract when they were administered with the full spectrum plant compound. And so these researchers concluded that CBD dominant cannabis-based nutraceutical oils are increasingly being used worldwide, with users suggesting they're effective in treating numerous ailments. Our data suggests that CBDA might have a more significant contribution to these beneficial effects than was previously thought. And I would absolutely agree with this. What I have seen is that having a CBD or a hemp-based product that contains some CBDA makes it much more effective. Now, here's a little review of the pharmacokinetic properties of THC, where you can basically see, if we're looking at THC administered orally, this is the middle slide here. The left is the smoking of THC, and the right is the intravenous. So this is really the important slide. And what you can see here is that the THC level actually stays fairly low. That's this the blood level of THC after oral administration, and this is in humans, it stays quite low. What goes up are two things. One is the 11-hydroxy THC. This is a metabolite of THC. And this next line here, this is active. So 11-hydroxy works a lot like regular THC. It stimulates the CB1 and CB2 receptors. And then there's also this high level of carboxy THC, which is an inactive metabolite that gets excreted and does not have a therapeutic effect that we're aware of. And then I just like to point out that well, I'll tell a quick story that I find really interesting. So back in 2013, the cable network news here in the United States aired a show about CBD working for seizures. There was the little girl, Charlotte Figi. Sanjay Gupta, the reporter, covered her story and showed that CBD was working for seizures. And so back then, everyone was thinking CBD, CBD, CBD. This is what we need for treating these refractory seizure cases. And I was thinking the same thing. At the time, because my practice was starting to get overwhelmed with these pediatric patients. And you can imagine when the mom comes in holding like a homemade bottle of some kind of an oil or a tincture and saying, how many drops of this should I give my child for this life-threatening condition? And I'm, feeling very uncomfortable with that. So I decided to set up a laboratory in my office so that I could analyze these artisanal and homemade compounds. And I had a case of someone that came in with a severe seizure condition, and the mom said, I bought this product at a local dispensary and it's working. I'm giving a small amount of it and the seizures are almost completely gone. And I got really excited and I said, all right, give me that bottle. I'm going to go test it and see what's in there, expecting to find some dosage of CBD that would kind of orient me to how to treat other patients. When I looked inside there, I saw no CBD. There was also no THC or barely any THC. What it was a very weak THCA product. It was dissolved in glycerin. It wasn't actually an oil. And there was a very low dose of THCA. And I barely believed it. I said, oh, how could this be possible? CBD is the thing we need to be using to treat seizures, not THCA. It's also interesting that the dispensary was selling this as a CBD product. They hadn't tested it. They just knew it was something that didn't get people high. And so they thought this must be CBD and not THC, but it turned out to be THCA. I kind of discounted that, but then it happened 2 other times where patients came in with the same product effective for seizures. So I published this in a case series, and this actually was referenced by some of those other animal models that I showed you, those groups that studied seizures in animals and were using THCA. So it just shows that we often go from the bench to the bedside, from the preclinical research to the clinic, but communication between clinicians and preclinical researchers are very important. And through my study in a series of email dialogues, I was able to help these researchers start looking deeper into THCA as an anti-epileptic agent. So now I am going to summarize how to implement this, how to consume raw cannabis. I think by now you realize that even low levels of THCA and CBDA could potentially be important in treating a wide range of conditions, from nausea and vomiting, metabolic disorder, liver injury, pain, inflammation, anxiety, depression. It's with cannabis, it always sounds too good to be true. So how do we implement this? I think the most important thing to consider is that if you're doing a cannabis extraction and formulation process that does not need to use high levels of heat and pressure, you're going to end up with at least some of these compounds. And in my opinion, that's preferred. So to all the cannabis producers out there, whether you're commercial or artisanal or homemade or whatever you're doing, try to limit the amount of heat and pressure you use so you do not fully decarboxylate these products. Even a small amount, 10% or 15% remaining in the acidic form, can make the product a lot more potent and also more broadly effective. Thank you so much, and I hope to see you in person next year.